video, we're going to look at wind production, how is it produced, and we'll look at an example which includes coastal wind. Then we'll look at windmills, and then finally we'll derive the power equation for wind power. So wind production, how is it produced? There's not a space in your notes. We're on page 4 of our notes, and I haven't given you any space to put the picture that I'm going to draw next. So you want to find find a good place to draw this picture, which shows us how wind is produced. Wind production. The sun, and right now I'm pretty much reading off of, or explaining with a diagram, the notes that you have on page 4. In the right column, second row. The sun sends electromagnetic radiation, and let me make the EM radiation red. Right? No, let me make it black actually. EM radiation is sent from the sun. It strikes the earth, the ground, and on the way passes through air particles. Right? Try and make them nice and pretty evenly spaced. It passes through those air particles, it strikes the ground absorbs it, so they go away. Right? Oh, well, the little arrow here goes away because it's absorbed, and as a result, the ground gets hot and kind of emits heat back up into the atmosphere. Now, when this happens, the air particles at the bottom, near the Earth, get hotter. Their temperature increases. If the temperature increases for these air particles near the bottom, then their volume will also increase. And the reason that their volume increases, you can think about it like this. They're moving faster. They start bumping into each other with higher velocities, and this causes them to spread out even more. But density, rho, is mass over volume. So if the volume increases, that means the denominator is increasing and density decreases. Things that are less dense, that have smaller density, right, they tend to move upward. Whereas things that are denser, that are more tightly packed, fall down to the bottom. And this is why hot air rises. This is what we mean in a lot of times when we say that heat rises. Right? The hotter air at the bottom here, we now understand exactly why it rises, as the green arrow shows. So yes, it rises. And when it rises, something has to fill its place. Something has to fill that space. Now, some of what fills the space is the air up here, which goes down. But there's something else that fills the space, especially on coasts. Sometimes air from the side can come in and fill that space, particularly when you consider the fact that not all of the air on the Earth, not all of that air is getting heated by the sun. Some of the air doesn't see the sun, and so that ground, this is the moon, right? So the ground below the moon has colder air, which can move into the side to fill the space of the hotter air. So the Earth's rotation produces some of this wind. The fact that some of the Earth is at night and some of the Earth experiences day allows for the winds to move to the side. Coasts allow this as well. This is the basic principle behind wind is produced. Hot air rises, and then other air fills its place. Whoops. Okay, now we're going to look at a more specific example briefly. Coastal wind. During the daytime, here's our sun. Here's the Earth. Here's the water. This is interesting. Remember that water has a high specific heat. the specific heat capacity is big, which means Q is absorbed, but the temperature don't change. The temperature doesn't budge, doesn't change. I'll use regular words. That's not the case for regular ground, like Earth, the stuff that makes up the Earth, right? The Earth doesn't have, the ground doesn't have a big specific heat. So here's the difference. The rays from the sun, the electromagnetic radiation, some of it strikes the Earth absorbs it, and it gets hot and produces this heat here. On the other hand, by the ocean, those rays get absorbed, and you might be thinking, isn't heat produced over the ocean because of the absorption? No, that's not right. There's no heat produced because, as we just said, of the high specific heat capacity of water. And this means now we have less dense air, this hot air is less dense. It will rise upward, and this air over here is cold air, relatively cold air, and it fills the space of the rising hot air. So it moves over into this space. Okay? This is how coastal winds are produced during the daytime. You know, so we could put a little note. This is daytime when the sun shines. Now, the nighttime effect is just a little bit more complicated, so I'm not going to go into great detail because we don't need to know it. But we will just draw a picture. The effect is reversed. Okay, this is how I'm going to explain it. I'm going to say the effect is reversed during nighttime. There, I just said it. So now the moon is out, no more sun. Maybe some stars, right? It's not a full moon. You don't have to worry about werewolves. So you're good there. Okay. In this case, now what we have is air over the ocean, which is hotter. So our hotter air is over the ocean. And the colder air now, this is our colder air over the ground. And here's the reason why the air is colder over the ground. When the sun goes down, the temperature drops, right? And the ground absorbs heat from the air. And that causes this air here over the ground to become colder. So the ground air gets colder, and relative to that ground air, this ocean air is warmer, right? I mean, the ocean air stays the same temperature at pretty much all times. The ocean air doesn't change in temperature. It's the same T as during the day. It's just hotter relative to that colder ground air. Good, okay. So the hotter ocean air, right, ends up getting pushed up, and the cold air takes its place at the coast, where we have the mixing of the two. So the hotter air rises, right? Heat rises. Things that are less dense rise. The colder air fills its space, and this causes, winds in the other direction. Okay, we are almost there. We are on to wind power. And specifically, we're going to look at windmills and wind turbines, and lastly, we will see the power equation for wind. Now, a windmill refers to, in general, the little nose-shaped thing along with the stem supporting it and all the electrical stuff inside of that. This part up here is typically referred to as the turbine, the wind turbine. Okay, that's how the phrasing works. The whole thing is the mill, and the turbine is just the nose plus blades plus what's inside. So what's inside of the turbine? How does this work? Well, I'm going to show you. I have a great diagram here. We have this, and you could draw some of this out into your notes, but we don't really need to know it. I think, maybe we do. We have blades, right? Here are the blades. They attach to this rotating hub called a rotor hub, and when those blades and the rotor hub turn, they cause this low-speed shaft to turn as well. So the blades are really connected to the rotor hub, and inside we have connection between the rotor hub and the low-speed shaft. Okay, get rid of some of this. Now, when that low-speed shaft turns, it causes some gears inside of this gearbox. We haven't shown the gears. The gears aren't shown, but there are these gears, and it causes the it causes the low-speed shaft to produce even much faster rotation in this high-speed shaft, and the high-speed shaft is thinner, right? So we produce higher speed rotation through the gearbox. That high-speed rotation of the high-speed shaft turns a magnet inside a coil, and that magnet and coil is positioned in the generator, right? So the magnet starts to turn, and this generates our electricity. So this whole thing is referred to as the turbine, which is a portion or a component in the windmill. Good. So wind power. Now, that covers wind power. That's our brief intro to. Sorry, this is our brief intro to windmills and wind turbines. We have rotation of the turbine, right? So kinetic energy of the wind is going to turn into kinetic energy of the rotating turbine. And that, so this is the first thing we have, here's the second thing. This produces electricity or electrical energy of the generator. Okay, if you can read that, you deserve a star. There you go. Whoops. Okay. Sorry there. The last thing we're going to do then is derive the power equation for a wind turbine. And you're probably going to need more space than I've given you on page 5, so you may want to get out another piece of paper and do it on a separate sheet. The first thing we need is a drawing of a turbine. And this is hard to do because it's a 3D drawing, right? But here's my turbine. It's rotating, and as it rotates, it sweeps out a circle, okay? And the radius of the circle is r. Wind passes through the turbine with some speed v. And what we're going to evaluate, what we're going to evaluate is over some arbitrary time t, kind of a smaller period of time, right? The wind will travel a distance d. So here's my distance d, right? There it is, what I've drawn with the arrows. And we know that the relationship between d, t, and v is this. Now, I need to be careful here. We're going to also use volume later, so I better make sure I use cursive v's so I can distinguish between velocity or speed and volume. Okay, so the wind travels a distance d over some arbitrary time t, right? And in that distance d, we could draw the volume of air that will pass eventually through the turbine. Okay. We know that the radius here is r. We know the distance d. And so the volume of wind, and here's how I'll do volume with these little feet at the top. The volume of the wind passing through the turbine in some arbitrary time t is just the area, the circular area, times the distance d, the height of this cylinder, right? Area times height. But we know that the area is the area is the area of a circle, which is pi r squared, so we can write the volume that way. Okay? But we should really specify that this is the volume in time t. Right? So if we wanted to know in general how many cubic meters pass through per second, we would take the volume and we would divide it by t, and it would equal this. Right? And the trick, which you probably can already see, d over t is the velocity. That's what this equation says. So we have just come up with an equation just by doing a little analysis here. We've come up with an equation that will be very useful for us. The volume passing through per time is equal to pi r squared times the velocity, or the speed of the wave, of the wind. The wind is what moves. The wind, sorry. Now what we're trying to get to eventually is an equation for power. So let's start with the equation for power. Energy over time. And we're going to first discuss the power of the wind's power. So I could write like wind down here if I really wanted to. And sure, why not? I do want to. Let me move this over. Whoa! Power of the wind is energy over time. Now the wind has kinetic energy. So this is the equation for the power of the wind so far. Right? But look at this. We have, over here, we have mass per time. Right? How many kilograms pass through per second through this turbine. As it turns out, we're going to be able to use that and relate it to volume per time. And you probably could guess how these two will be related. It'll involve density. Right? So let me first, just so I understand exactly what I'm doing here with the wind, the power equation, I'm going to write this as 1/2 mass per time v squared. And whoops, I need my cursive v there. Okay. And now I'm going to substitute in for m over t using v over t. We'll see that next. We know that the mass over time here, let me do this in green. We can rewrite mass over time because mass is equal to volume times density, like that. Right? If you want to see that that's true, here's our equation for density. And so clearly mass is equal to density times volume. So all I've done here is I've taken the mass and I've replaced it with volume times density. Okay? And as we know from before, v over t, this part of our term, is pi r squared times the velocity. So that's v over t, but then we had this extra row here the density. And so what we've just done is we've come up with an equation for mass over time. It's pi r squared times the speed times the density of the air density. So if I look up here, I'm going to get rid of m over t in my power equation. I'm going to replace m over t with pi r squared speed times density. And when I do, I get something beautiful. So beautiful. Let me move this. Let me just get rid of this. No, I'll just move it down. So again, you've got it in your notes. M over t we can rewrite as pi r squared Vp, rho. Right, I've replaced m over t with the thing in parentheses. I hope I'm not calling it, I hope I'm not calling this p. That's the Greek letter rho, which looks kind of like a p. So our final step is to join together, combine the velocity factor. And let's see then, hang on a second, how do we write this? In our book, in the book we put density up front. So I'm going to rearrange then. Let me get rid of that, not show that. And the way we write it, more commonly, is we say the power of the wind is rho times the, 1/2 rho times the velocity times pi r squared velocity cubed. So there is our final equation for the power that is supplied by the wind. Now there's an interesting fact about this equation, right? This is the power of the wind. You might be thinking that we can harness all of that wind power in our we can harness all of that wind power in our turbine here, right? As it turns, the power of the wind is 1/2 rho pi r squared speed cubed. So surely we can capture pretty much all of that power if we have a really efficient turbine, right? That is not true. Even a perfectly efficient turbine would not be able to capture all this power. The most that we can get, and I'll explain why in just a second, the theoretical maximum amount of power we can get from the wind is around 59%. 59% of the power of the wind's power can be extracted by the turbine if the turbine has no energy loss whatsoever. Okay. And here's the reason we can at most get 59% out from the wind. The wind travels forward, and in order to spin the blades, it has to actually pass some over the blade and some under the blade. It has to be split by the blade. And that means that while it has kinetic energy before striking the blade, in order to actually turn the blade, it has to have some kinetic energy at the end after passing over the turbine. If the wind were to just stop, it wouldn't get split by the blade. Oops. It wouldn't get split by the blade if it stopped, and it wouldn't cause that blade to turn. So we need some of the kinetic energy to still exist after it has turned our turbine. And this is why the most we can get out, the maximum efficiency, the maximum power that we extract is 59%. That's the theoretical limit we can get from the wind. When everything is running as well as it could possibly go, right? We get 59% out. Good. Now, there's one last thing to say. Obviously, when we're deciding where do we put our turbines, turbine placement, or let's say windmill placement, since the whole thing is the mill. Windmill, one word. There are two big factors in how we decide windmill placement. One, we want lots of wind. That's pretty obvious. We want lots of wind. But there's another factor that we consider. These turbines oftentimes have long tails, right? Something like this, right? So they have these tail parts here, which allow the turbine to rotate, like around the support, right? So it allows it to rotate, around the vertical axis so that it's always facing the wind. But the problem with rotation like this is that we lose energy to friction because this turbine is so heavy. This is a big, heavy thing, and we want to avoid rotation due to direction changes in the wind. So we find places where the wind tends to just flow all in one direction continuously for long amounts of time. That's the best place to put a windmill. So, as you could probably guess, you get that kind of wind around oceans, around shores. Right? The coastal winds that we learned about before provide for the types of conditions which allow for high efficiency of windmills.